Are we live? I hope we are. Looks like we are live. I can turn my webcam on. Welcome. Hello. Happy Halloween. Hello everyone. Welcome to the OneClass channel. My name is Millan and I am a software engineering student at Carleton University here in Ottawa, Canada. Today we will be going over some commonly asked questions in mathematics at mostly the high school level. If you need some homework help or you need some tutoring, check out the links in the description below. Now it is Halloween, so I wanted to make today's stream a little bit more special, so I did dress up in my Halloween costume. I am a crossing guard, because gotta make sure no one ever crosses me, or when things get crossed, they are crossed properly. Alright, cool. Let's start off with some mathematic magic. Sounds like a fun time. Okay, awesome. So let's take a look at this question. The first question that we have on the stream today. The question asking, what is the discriminant? Now, that might be an intimidating looking word, but it is really fairly simple. So let's think about, what is a discriminant? Well, the discriminant helps tell us how many real roots our quadratic has. Now, to clarify what we mean by a root, that's an x-intercept. X-intercept. Okay, so let's go over some examples of what are the possible number of roots that we can have. And then we'll get into how the discriminant can tell us what's going on, and how the discriminant can tell us how many roots we can expect. So suppose we have an xy grid like this. If we got the red parabola here, no roots. You know why it has no roots? It never even comes close to touching the x-intercept or the x-axis. So you can't have any x-intercepts with that. No roots for you. Okay? Now parabolas are sometimes looking the other way. Let's do a green one. And it's possible that you'll have a parabola that looks like this. So here, there's only one x-intercept. There's only one point, basically at the tippity top of the hill of the parabola. Or, I mean, if it was the other way, it would be like the base of the valley of the parabola. But regardless, if it only touches the x-intercept at one point, well, that is a one root situation. Okay, and the last possibility, I'll make that blue or purple, like a blueberry. Yep, makes sense. So the last case is when we have two roots. Now, of course, you know, it's looking like a hill, like opening downwards, but it would be just the same if it was opening upwards like a cup or a valley. We would see that since it has two distinct places where it intersects with the x-axis, we know that this is going to be a two-root situation. Now let's think, would it be possible to have a three-root situation? Absolutely not. Because no matter which way you flip these parabolas, move them up and down, you'll never be able to get three intersections with the x-axis. And of course, we can't, like, if we're trying to go -1 roots, that question doesn't even really make sense. So we know that all quadratics can have a maximum of 2 roots, or they might have 0 roots, or they might have 1 root. So these are our possibilities for roots. Root number possibilities. One. Nope. Gotta consider 0. 0, 1, or 2 roots. Never 3, never 4, never more than 2, and definitely never any negative number of roots. Let's not even think about that. That's a little too wild. Okay, that's a lot of fun stuff. Now, how does this discriminant tell us how many roots there are? Okay, so this is the discriminant, or first let's talk about quadratic formula. So quadratic formula will tell us where the roots are. Okay, so we have quadratic formula. Quadratic formula tells us the x-intercepts. And the quadratic formula looks a little something like this. X equals. I'm just going to verify this. Make sure I don't get anything wrong. Because, no matter how sharp you are with your math, if you copy down the equation wrong, you'll be in trouble. So we got negative b plus minus b squared minus 4ac over 2a. Okay, quadratic formula, super duper useful. Just keep it in mind. I'm gonna extend this the page horizontally. Okay, no worries. So this is what our quadratic formula is. And this tells us what our roots are. Now let's pay close attention to this little plus minus here. Okay. Now there's going to be situations where we're going to have 2 possible roots, and this plus minus will give us it will give us this one, and it will give us on this blue. I'm trying to make my brush a little bit more visible. See this one and this one. We can find those out because of the plus minus. But what we're mostly interested in for the discriminant is right here. Okay, so going back to my pencil. So this is quadratic formula. Oops, let's get the brush instead. It's a little thicker. This is the discriminant. Discriminant. It looks a little something like this. It's basically just what's underneath the root of the quadratic formula. So it is really just b squared minus 4ac. Okay. First, okay, let's rewind a second. Let's figure out what is our a, b, and c. So our standard form of quadratics looks a little something like this. Y equals a x squared plus b x plus c. This is where a, b, and c come from to put it into this equation, into the discriminant. So you want to get your quadratic in standard form, and then you extract your a, your b, extract your c from that equation, and send it down there. Okay. Now, when you do this calculation, there's going to be a couple of possibilities. Either this is a positive number. This could be a 0. Or this could be a negative number. If it's positive, that's 2 roots. 2 of them. 2 of them. Don't forget it's 2. It's not 1. You got 2 roots. 2 roots. Roots, there's 2 of them. If you got a positive number, if this is exactly 0, we're going to have a 1 root. Oops, I'm going to rewrite root because that kind of looks like riot, which is absolutely not the same thing. Stay close to your roots. If we got a 0, that's 1 root. And if we got negative, no real roots. Once you go a little bit deeper into your mathematic magics, you'll see that you'll have some complex roots, but for these purposes, no real roots. But you can just write no roots because real or not real, imaginary, you don't need to worry about that for now. Okay, so let's see what will happen to our quadratic formula when we have a... So consider this. The discriminant is always under the root, right? So if it's positive, we get a regular square root. So this is just a regular square root. A square root, and that will give you a value, and that's let's say the discriminant equals, or root of the discriminant. Let's put this under the root, is equal to positive number. Okay, now if our discriminant calculation is 0, b squared minus 4ac, if that whole thing is 0, we got 0 under the root equals 0. Okay, now if it's negative, hey, what happens if you take a negative, the square root of a negative number? You know what you get? You get trouble, because this is complex, and if you're just learning about discriminants, you probably don't need to worry about complex numbers for now. So this is just like no roots, or not real. It's not even real. Where are the roots? They're not real. They're imaginary. It's incompatible with, for now, let's just say the square root of a negative number is not real. Not even real. I don't want to see nothing about that, okay? So imagine this, okay? So if it's positive, we got a regular number here. So we got like b, negative b plus minus a regular number divided by a. That's going to give us 2 options, meaning 2 x values where we have roots, or x-intercepts. So that's what's going to happen if we have a positive number in over here. Under the b squared minus 4ac, under that root, positive number, we're going to have 2 options for x, and that's going to come out in our quadratic formula. Let's say we got 0. We got an entire 0 under the root. We got minus b plus minus 0. Psh, ignore that. It's just going to be negative b over 2a, and that's going to be the only root that matters in the event that our discriminant is 0. Now, if we have a discriminant under the root here that is negative, that's trouble. That's not even real. We can just say discriminant is negative. We ain't got no roots nowhere around here. I forgot my roots if we got a negative discriminant. Okay, so that is why discriminant is useful. It can basically tell us how many roots we got, depending on the positiveness, the negativeness, or the zeroness of the discriminant. Sounds good? Sounds good to me. This is a fun time. Yeah, mathematic magic. It's a beautiful thing. And I guess they do have an example here where we get a positive discriminant. That would correspond to a double root, or not double root, a pair of roots for that particular curve. And if we were to plot this with a equals 6, b equals 10, c equals -1, that would be a 2-root situation, because that discriminant is positive. Oh, and they graph that out. 1 root, 2 root, red root, blue root. Looks good. So the above solution is good. Is good. Okay, I'm just gonna clean off my whiteboard. And I'm going to expand this a little bit because we need more space like astronauts. Awesome. So that is a question complete. Awesome. So this is the next question on the menu today. What is the step? What are the steps for simplifying radicals? That's rad, bro. What is a radical in the first place? Radical, I mean, some people say, that's radical, meaning that it's, super out there or super cool. In math, radicals are roots. Some of them look like this. We got like, something, maybe x. That's a square root. And maybe we have something like this. So it could be like that. That's a cube root. And, well, we might not have just 2 or 3. By the way, if you don't see anything there, it's a 2. Just know that it's a 2 because square root is probably the most common radical that you'll see, but it is possible that you'll see other roots or radicals with other numbers here. That just specifies like, the root. If you got n, that could be any number that you choose, any real number that you choose. That would be an nth root. Like if n was equal to 5, you'd say the 5th root of x. That's essentially what it's meaning. Okay, now what you can do is that roots are essentially exponents with fractions. So the square root is equal to x to the power of 1/2. The cube root is equal to x to the power of 1 divided by 3, 1/3. The nth root, well, that will be x to the power of 1 over n. And n, like let's say, let's say for example we had n equals 5 here, the 5th root. It would be x to the power of 1 over 5, or x to the power of 0.2, whichever suits your fancy. Okay, that's a great way to start simplifying radicals. Another thing that you can do if you have a radical is if you have things inside the radical that are raised to the same power as like the thing that's on the outside of the radical, you can move them out. So let's say we have a situation like this. You can also definitely factor out the things inside. This will typically be a helpful thing. Let's say we got like the square root of 18. We know that 18 is equal to 2 times 9. Hey, what do we know about 9? That looks like a square type number to you? Looks like a square type number to me. We should see that this is just 2 times 3 squared. 3 times 3, is that 9? Sounds about right. Studied my times tables for many times on many tables. Okay, now you see how this radical is the square root. Like, there's an invisible number here, but that, like, we can see the 2 there. It should be there, but we don't need to write it because mathematicians are lazy. So we can look inside. Hey, is anything inside of there squared? Oh, there's a 3 squared in there. That means we can pull it out and remove the square. And this is equal to 3 times the root 2. It's basically moving it out here and remove square. Okay, now of course if this was like a 3rd root or an nth root, we would do something different. Like instead of, we'd be looking for cubes inside. So maybe an example of that is like, I'm trying to think of a nice cubey number. 54. According to my calculations, 54 is, let's say that's the cube root. According to my calculations, 54 divided by 2 times 27. That's 54. Yep, sounds about right. So the cube root of 2 times 57. Nope, not 57. 27. My apologies. The 2 and the 5 do have some similarities in their appearance, so please forgive that. Now, is anything inside of their cubed? 27 seems like a cubey number. So what's 3 times 3? 9. 9 times 3? 27. Whoa! It's almost as if 27 is 3 to the power of 3. So it's like 2 times 3 to the power of 3. Now we can bring this outside the radical, and we can remove the cubed power as we move it out, because we're doing the cube root, we're looking for things that have cubes underneath the root, and we're going to move them out there. So as the 3 moves out, it loses the power of 3 because of the cube root. And hey, would you look at that? We just get 3 times the cube root of 2. And that would be our final answer. And you send that through your calculator, I'm sure you'll find that this looks good. Cool. Now that's typically what radicals are. When you get into calculus, you'll see that converting them into fractions instead of keep them as roots could be a useful move to do. But yeah, let's actually see what their examples are. Okay, so the example that they have here under the root is 9 times a to the power of 4 times b to the b squared times z to the power of 6. Hey, they recognize all of those are a little bit squarey. Like they're all something squared, right? 9 is 3 squared, and obviously the variables with their exponents, there's something squared. So they wrote them as a square, and they moved all of them outside of the root. Underneath the root, it's just 1 left after you factor out everything else. The square root of 1 is 1. They don't really need to write that, so they can just leave it as is, as 3 times the square root of a to the power of 4, so that's a squared. B, it loses that power of 2, and z, it to the power of 6 becomes to the power of 3, because the square root of to the power of 6 is to the power of 3. So that's another thing with like exponential rules. Multiplication is kind of how it works. Also, if you converted the square root into a power, and then you did all of those to the power of 1/2, like it's just multiplication, and you would see that it all works out good. Okay, so the above solution is correct, and that's a good time. Solution is correct. Spooky. It'd be very spooky on Halloween if it was not correct. Happy Halloween again. Spooky season. Okay. The next question that we got on the menu. What is the formula for the sum of the first n terms in an arithmetic series? Let's rewind for a second, okay? Before we handle this question, what even is an arithmetic series? Or sequence, my bad. An arithmetic sequence is a set of numbers where there is every term is a little bit bigger than the previous term, but only by a certain amount. And the amount, like you're always adding to it. So an example of an arithmetic sequence. Arithmetic sequence. An example would be 1, 2, 3, 4, on and on and on to like 57, 58, all the way up to, I don't know, however long you want to go. These arithmetic sequences can go on for a very long time if you want them to, but we don't always want them to because we're lazy mathematicians. but that doesn't mean we're dumb. That just means that we know that we don't necessarily want to put in effort to solve things if there's an easier way. So this is an example where we're adding by 1 each time. We could have other examples where we're adding by maybe 5 each time. So like 5, 10, 15, 20, 25, on and on and on. It's maybe like 1,000, 1,005. Like we can go for forever, but you know, it gets less and less exciting every term. But this is typically what you want to pick up from arithmetic sequences, is that every term is a specific amount added to its previous term. Or if you're at a term, to get the next term, you're just adding by a certain amount, and that certain amount will be always the same everywhere in the sequence. So like to go from this term, the 1,000 term, to the 1,005, we're adding 5. Same thing with all of the lower level terms, like the earlier terms in the sequence. Like we're just adding 5 to find the next thing. Okay, now how do we find the sum for the first n terms? Well, we could just add them up, but that doesn't seem like fun to type in a calculator, and if you press one button wrong on your calculator, you crash the whole boat. So you want to avoid doing delicate calculations like that where you're typing in a lot. Typically you want to type in as little as possible into your calculator, because every time you push a button there is a risk, a small risk hopefully, but there is a non-zero risk that you'll push the wrong button and crash the whole boat. So a nice way to find the sum of the first couple terms in an arithmetic sequence, the sum of first n terms, like it could be the first 5 terms, it could be the first 5,000 terms. You know, it depends on what you're feeling on the calculation or what your application requires. So the sum of the first n terms in the, let's just call it the A sequence, the arithmetic. Arithmetic might sound like error, but we will not have any errors if we calculate it this way, as opposed to the the arithmetic errors that you see if you type it into the calculator. Yeah, don't want none of that. The sum of the first n terms is this equation. So it's the sum of the first n terms so we can represent that with the big S and a subscript n. S for sum, n for, you know, the n terms. That equation is just going to verify to make sure that I got this good. So it is the number of terms, n, divided by 2, or I'll write it out in full as like the words, and then I'll write them out as symbol. So this would be num of terms, divide that by 2, and multiply that by the first term plus the last term. Okay, so the number of terms is n. Let's actually rewrite this to be a little bit shorter. Equals n over 2, n being number of terms. Fairly straightforward. Multiply by the first term. That is simply, that depends on what your first term is, but I mean, if they give you an arithmetic sequence, you kind of got to know what your first term is. So that will be, let's call that A1. A1, so that's the first term. First term value should be given. Plus, how do we find the last term? Well, let's think about this for a second, okay? To go from term to term, we're adding by a certain amount every time. So to get the next term in like the low sequence here, or in the sequence here, to go from term to term, we're adding 5. Like we start at 5, that's our first term. Our second term is 5 plus 5. Our Our fifth term is going to be 5, our initial term, plus 4 times 5, so 20. Okay, so to calculate our last term, it will just be the first term. It will be the sum of the last term is going to be n minus 1 multiplied by d. N being the number of terms that we're taking an analysis of. Oh, it should be like 2 times first term. Yeah. I think it should be for 2 times first term. Let me double check this because I do not want to say nothing wrong and have anyone include that into their calculations. I think it is just first term, and the last term is n minus 1 times d. D being like what you're adding each time. Okay, I actually think it is 2 times the first term, but we'll run it through an example and we'll see if it works out. Okay, so let's do it for our first example here. So let's use this equation for, like, if our sequence is 1, 2, 3, 4. We know that n is equal to 4. We know that d is equal to 1. We're adding 1 to get to the next term. We would expect our sum. We're expecting our sum, our Sn, to be 1 plus 2 plus 3 plus 4. That's good. We're going to expect 10. And I guess our A1, our first term, is 1. Sounds about right. Whoa. Okay, let's run it through the equation and see if our equation is good. So S of n, we expect n divided by 2 multiplied by 2 times A1 plus n minus 1 d. Okay, S of n, our n is 4 over 2 times 2 multiplied by 1, because 1 is our first term, plus n minus 1, so that's 4 minus 1, and multiplied by d, that's just 1. Okay, so let's do some quick math. So we got 4 divided by 2, that's a solid 2. 2 times 1, that's going to be 2, plus 4 minus 1, that's 3. And then 3 times 1, you know, looks like 3 to me. So we got this. Inside the brackets, 2 plus 3, that's 5. 5 times 2, 10. And that's exactly what we would expect. Okay, so this is the equation, or the formula that you should use if you're trying to find the first n terms of an arithmetic series. Now, you know, we can double check our expected value with like a small sequence like this, because it's fairly easy for us to like mentally add this up. But you might get some very spicy arithmetic sequences where, let's say, n is going to be 1,000. You can't necessarily trust yourself to be adding them all up unless you write a program to do that, but that's a whole nother thing. So use this equation instead. We just proved that it works good for 4 terms. I assume it definitely has to work good for 40 terms, 4,000 terms, you name it. Just make sure that you're able to extract your values here. So the n, that's just the number of terms. D, that's what you're increasing by to go from term to term. And A1, that's just the first thing the first element in the sequence that you're looking at. Sounds good. So D, I mean, what you're adding from term to term, also known as the common difference. That was the vocabulary I was looking for. But yeah, you try this, you'll do good. It'll be a lot easier. Like, let's say you got 1,000 terms you want to add up. This is the way to go. You don't want to be manually doing that math. It takes too long. Sounds good. So the above solution is good. Okay, let's clean that whiteboard up. Okay, a very nice question that we got here. The next question on the menu: how do we solve a natural logarithm of x and that's equal to 7.25. Okay, now let's talk about natural logarithm for a second first. This is really just log base e of x is equal to 7.25. And what log basically is saying is that the base here, that's the base to the power of the result, 7.25 in this case, is equal to x. This is essentially like the secret sauce to finding logarithms. In this case, the base is E, Euler's number. Yeah, Euler is spelled with a EU. Euler's number. Now this is a very special and spicy number in mathematics. You'll see it a lot. It's 2.718 on and on and on. It was originally calculated by, Euler himself. He was trying to figure out some stuff about compound interest, and he named a number after the magical number that he found, because no matter how much you increase the compounding period, like if you're familiar with compound interest, compounding period is like how often you're increasing. Even if you do that like every nanosecond, every microsecond, or every microsecond, or any picoseconds, like you're doing that extremely frequently, you'll never get more than a return rate of like Euler's number. Okay, but that's not particularly important. What is more important is how we can use this little squared off section and use that to solve this. Okay, so we know that we can essentially raise the power, or this is essentially what the equation is saying, or what logarithm means, just like a little bit rewritten. So the secret sauce that I want to tell you is that e to the power of ln of x is equal to x, and so e to the power of ln x, that's just the left side becoming the power of e. So we have to do that to the same thing to the right side. So e is going to be the base to the power of 7.25. And that's what x is. So let's run that through the calculator. I got my trusty Texas Instrument TI-84. It was a gift. That's been rocking strong with me since 2011. It was a gift from my big sister. Thank you, big sister. Now we got to find Euler's number, E. I'll find it fast, I promise you. Aha. E to the power of 7.25. Yep. Is, wow, that's a big number. 1,408.104848, on and on and on. Seems reasonable because, E is about 2.718. So if I were to do like an equivalent 2.718 or so to the power of 7.25, we also expect around the same, I'm not sure if that's mirrored or not, but it is also like 1,400. So Yeah, it looks good, looks reasonable, looks beautiful. Mathematic magic, it's a good time. And the answer that is given here is absolutely correct. Now, it is probably better to leave your final answer looking like this as the E. Because like when you introduce the decimals, and that's a lot of decimals, you're going to lose precision if you cut them off, so it's better to just leave it as something exact, which is just e to the power of 7.25. Sounds good, sounds great. I think it sounds great. Logarithms, natural logarithms or regular logarithms, they're pretty simple once you get the hang of them. So the above solution is good. Okay, awesome. Okay, the next question that we got on the menu today: what are consecutive integers? Well, let's first rewind a second. What is an integer? An integer. Whoops, gotta get the brush. Integer. Don't say integer, because you'll make me growl. You'll make me mad, and I'll be like grr if you say integer. That's not the way to say it. Integer is a number. Can be plus, can be minus, can be 0. No decimals. Oops. So let's give some examples. 21, integer. 21.0, not an integer. Even 0.0, you don't want to. No, integer, not gonna appreciate even a 0.0. Unacceptable. Not integer. Let's say we have -5. Yup, integer. -5.5, not an integer. Nope, not even close to an integer. What about 0? 0.0? Nope. Not integer. And my reaction to asking if this is an integer or not is the same as what that looks like. Yep. So, and just 0 by itself, definitely integer. So, we know what an integer is. If you see a decimal, yeah, not an integer. Get that out of there. Now we got to think about, what does it mean to be consecutive? Consecutive means directly after. So, consecutive integers means that one is immediately after the other. So, what's the next integer after 21? I don't know about you, but I'm feeling that it's 22. And after that, 23. Can you fit any integers between 22 and 23? I don't think so. The only way that you could fit any number between 22 and 23, that's with some decimals. And what do we say about decimals? Get them out of here. They are not integers, not invited to the party. So we know exactly like what consecutive integers are, just because like we're going to add 1 to an integer and it's going to be consecutive. So you can tell if integers are consecutive. Whoop. See, that's why I teach math and not spelling. Consecutive. If you add another F to your if, that means if and only if. It just means like a stronger if. You'll see that a lot in math. Integers are consecutive if and only if the difference between them is 1. So let's do some examples. 23, 24, consecutive. Because the difference is 1. 22, 24, that's, yeah, the difference between them is 2. That ain't 1, so not consecutive. Okay, some other examples. Let's say we got negative 5, negative 4. Well, what's 1 bigger than negative 5? Negative 4. It's not negative 6. Negative 6 is one smaller than negative 5. Keep the number line in mind. It's a good way to visualize. Like, bigger always means towards positive infinity. Smaller means towards negative infinity. So negative 6 is not consecutive to negative 5, but negative 5 is consecutive to negative 6, if that makes sense. Okay, so negative 5, negative 4, consecutive. Okay, my spelling is, I think my brain is just thinking in French, because French got QUs a lot more often than English. Oui. What about negative 1.0 to 0? Oh, wait a minute here. This is not even a proper question, because you see that point 0? Get that out of integer land. You're not invited to the integer party. This is like broken. This is not consecutive. Not consecutive integers. Because that's not even an integer. Not int. But we got negative 1 and 0. Those are consecutive integers because we got rid of them decimals and we're back in integer land. We're partying. We're happy. No decimals here. Consecutive. Sounds good. We got some examples here. Consecutive integers are that follow each other in order. And a similar type thing if we're talking about consecutive odd or consecutive even numbers. If you specify that it's odd or even, you just know, like, it's the same pattern, except the difference between them would be 2, because even numbers are every second number, odd numbers are every second number. They switch places, like a alternating pattern. So in that type of situation, you would have a difference of 2. But you just gotta kind of have a decent sense of what numbers come after what other numbers, and I think that pattern is pretty easy to see the more you get practice with numbers. Fairly straightforward stuff. Okay, so I think we can mark this question as the above question is good. Awesome. Now, what's the next thing that we got in our menu? What are the numerator and the denominator of a fraction? Well, let's talk about what even is a fraction in the first place. A fraction is something that is a partial component to a whole. Fractions look like this. On the upstairs, we got numerator. On the bottom, or the downstairs, we got denominator. The nice way I used to remember denominator, D, downstairs, D, both start with D, both go downstairs. That's probably the best way. That's how I used to memorize it, but yeah, could be a useful thing. Denominators are downstairs on the fraction, and what's on top is the numerator. Okay, so the denominator is total number of things in a whole, and this is like current number of equal components to a whole. Okay, let's say we got a pizza party and we got a circular pizza that looks like this. We got a pizza party and here's our circular pizza, and maybe we want to cut it down like this. like that. Okay, now let's say we're having this pizza party. There are 4 slices in total. So total number of things in this whole pizza, there's 4. So 4 in this case, in this pizza party. Now, let's say that I'm very hungry and I munch and I eat very good and enjoy thoroughly this 1 slice of the pizza. I just ate 1, so the 1 that I just ate would represent the numerator. So this is I ate a slice. That translates to, as a fraction, I ate 1/4 of the pizza. Okay? Now, if I ate 1 slice of the pizza, how many slices of the total pizza did I not eat? I did not eat 3 slices of the pizza. There were 4 total pizza slices, but I did not eat 3 of them. So the numerator in that case is 3/4, because there's still 4 in the total. That's the denominator. Is always going to be pretty much going to be constant. And the numerator is how much we're kind of like taking account of for this current statement. So the number of pizzas that I did not eat is 3/4. So 3/4 pizza not eaten. Okay, so denominator is downstairs. That represents how many things make up a whole. On the upstairs is the numerator, and that is the number of things that we're currently thinking of. So, we got 2 different situations in this example. Eating the pizza, I ate 1 slice, so that's just 1/2. That is, 1/4 of the pizza. There's 4 slices in total, and I ate 1 of them. So 1/4 pizza eaten by me. The number of pizza that was not eaten by me, well, there's 4 in total that were originally available. I ate 1. There's only 3 that are not eaten so far. So 3/4 of a pizza, 3/4 pizza, not eaten. Okay. Yeah, and it doesn't have to be circular pizzas like this. You can have rectangles. It doesn't even have to be pizza either. This could be pie. This could be cake. This could be the sun. And we're talking about the fraction of the mass of the sun. We like to start in easy day-to-day examples, but you can use these same mathematical principles to do some very advanced scientific procedures. Maybe eventually you're doing something like the amount of fuel in a fuel tank to drive a rocket ship to Mars. You're going to have fractions because, a fraction of the fuel tank is going to be used in, the takeoff. Now in the propulsion across the space land, it's going to be a different fraction of the fuel. Like, this stuff is useful in many, many industries. So just know that the denominator is the number of components that make up the whole, and the numerator, the upstairs, is how many we're currently referring to or looking at. Sounds good? Sounds good to me. Okay, verify the solution. The above solution is good. Awesome. We can have a pizza party to celebrate this. Okay, the next question that we got on the menu: expansion of polynomials. Expand x minus 5 multiplied by actually I'm gonna write this a little bit lower just because I want to have some space on top to draw some stuff. Okay, cool. X minus 5, x plus 2. We gotta expand these brackets out. Okay, now when you're expanding, this is the strategy that you typically want to use. So we're going to multiply like the first and there, and then we're also going to multiply the first and the second. And then in blue, we can take care of the second times that, the second of the first times the first of the second, times those. Okay, and these are going to be multiplications that we're doing. Okay, so let's do the first two red terms. So we got x squared. The signs are very important. So you see how x here is positive and that x is positive, so it's going to be positive x times positive x. Okay, that's this first arrow here. Actually, I'll do these all different colors. So maybe green for this one. Plus, we have 2 times x, or x times 2. It's just more of the convention to have the number in front. That's called the coefficient. But we have x times positive 2, so that's plus 2x. Okay, then we can move on to our first blueberry line. We got negative 5 times x. Now, that negative, extremely important. You forget that negative, you're in trouble. Okay, so we got negative 5 times x, negative 5x. And the last one, I'll just draw another color on top of that. Maybe we got purple. Negative 5 times 2. Don't forget the negative, you'll be in trouble. Negative 5 times 2, what's that? Negative 10. Negative 10. Okay. Nice different colors to show where all of this comes from. All of those are multiplications because like these brackets side by side means multiplication. It may be the case that up to this point you've only seen multiplication like with an actual x, like the x for multiplication. But since we use x as a variable, we're going to try to move away from using x's to show multiplication. We're going to just like put things beside each other to show multiplication. Just because x is a variable name, and it will get confusing if we have like, you know, x times x. Is that x to the power of 3 or x to the power of 2? It gets confusing. So we're gonna, in math, we're gonna start to get away from using x to represent multiplication. Instead, you do something like that. So variables beside each other, that's just multiplication. Awesome. So now that we have this, we can collect like terms. And like terms means that they have the same x attached to them. So we only got one x squared. Only x squared term. Here we got, these are x terms. And these are just, well, I guess in this case we only got regular numbers. So let's combine our like terms. In this case, our x terms are the only things that have more than one term. So that's just going to be x squared 2x minus 5x. How many x's is that in total? We got 2, but we're taking away 5. That's negative 3 x's in total. So negative 3x. And the regular numbers, well, that stays the same. There's only one regular number, and we're going to keep it that way. So we got negative 10. Cool. So that is our expanded version of the equation. And then we can have a celebration that we found it and that things are all looking good. Okay. Now their distribution is pretty much the same thing. It's just they drew it out differently. I prefer to have it this way. If you draw different colored like bars to show the multiplication, that can be a helpful tool. But eventually you'll get so good at this that you can just look at it and instantly come to the expanded version. It takes practice, but you'll get there eventually. I bet if you like math. So here the above solution is good. Awesome. Super duper cool. Okay, next question that we got on the menu here. How do we graph the parabola x equals y squared minus 4y plus 3? Now, this is a little bit this can be intimidating at first, but It really isn't. Because if you look closely, this follows the parabola format, and we're just not used to seeing like y squared. We're typically expecting to see x squared and stuff like that. But that is no worry. We can still handle this. Now let's see if we can factor out, or if we can factor the right side of the equation to see where our y-intercepts are. Okay, so now we're pretty much looking for something that multiplies to 3. Or we're looking for a pair of numbers that multiplies to 3 and adds up to a negative 4. So 3 is a prime number. So we know that there are really only 2 possibilities, since it's positive 3, that we can be adding stuff, that we can be multiplying stuff together to get positive 3. So we either have 3 and 1, or we have negative 3 times negative 1. Because those will both give positive 3 here. And added together, they have to be negative 4. Well, those added together are positive 4. So yeah, they're disqualified. See you later, alligators. Adds up to negative 4. It's got to be negative 3 and negative 1. So those are going to be the terms that when we have the factored out version, we have y minus 3, y minus 1. Does that make sense? Let's try to multiply this out. We get y times y squared. And we get negative 3y and negative 1y together. That makes negative 4y. Hey, that looks good. And then our last term is multiplied together. Negative 3 times negative 1. That's positive 3. It's almost like this always works. Ain't that beautiful? Okay, so now that our equation looks like this, we can more easily find our y-intercepts. So we want to see, when does x equal 0? X equals 0 when either one of these terms is equal to 0. So either when this whole term is equal to 0, or this whole term is equal to 0. When either one of those is equal to 0, x will be equal to 0, because it will 0 the entire right side of the equation. So x equals 0 when y equals 3, and when y equals 1. Okay? So that's cool. Y equals 3, y equals 1. Like when y equals 3, 3 minus 3 is 0 times negative 2. Or I mean 0 times 2, that's 0. And then when y is equal to 1, this term becomes 0. And that term becomes 0, and this whole thing is 0. Okay, so these are a couple points of interest. This gives us 2 points of interest. We got x is equal to 0, y is equal to 3, as well as x is equal to 0, x equal to 0, y equal to 1. Those are 2 points of interest. And we're also going to want to find, we know that, hey, these are our 2 x-intercepts. Or not our x-intercepts. These are our 2 y-intercepts. We know that the highest point, because like, okay, so this is basically going to be a parabola, but it's like horizontally shaped. And they actually have a graph of it in the answer. We know that if we have 2 x-intercepts, or 2 intercepts in a parabola, 2 roots, these are the roots. Roots, like the sweatpants, but we're not going to sweat it. We got our smarty pants on. We got 2 points of interest. Those are our roots. We know that the peak, basically like the tip of the parabola or the bottom of the cup of the parabola, is going to be exactly halfway in between them. So when y is equal to 2, because halfway between 3 and 1, what's in between 3 and 1? Exactly halfway. It's got to be the number 2. Y equals 2. that's going to be the peak value. So let's see that what x is when y is equal to 2. So we'll have 2 minus 3. Multiply that by 2 minus 1. Some quick math. 2 minus 3, negative 1. Quick math. 2 minus 1, that's 1. X is equal to negative 1. So that's another point of interest. This is like the peak, sometimes also known as the critical point. But that's more like when you get into calculus that you'll learn about that. So what's there? The peak or the critical point is going to be when x is equal to negative 1 and y is equal to 2. Okay, these are the most important points of interest when you're drawing a parabola. Is the roots or the intercepts. Is these. Sometimes you won't even have roots, and that is a possibility. You'll use quadratic formula to figure that out. And the critical point, where that parabola turns, there always has to be 1. This is going to be the tip of the parabola if it's hill shaped, or it's going to be the base of the valley if it's like cup shaped. So draw in these points of interest, and you can really like connect the dots. Like, of course, you can get as much precision as you want by finding different x values or subbing in different y values, finding out the x and calculating it like that. But once you draw these 3 points of interest, you can pretty much connect the dots, and it's not that important. Like, you want to generally follow the pattern, but if you're drawing this by hand, these are the main points of interest that you just want to connect them, and everything else should be good. Sounds good. Now this solution, it looks right. So we do have our points like x equals 0, y equals 1, x equals 0, y equals 3, and x equals negative 1, we got 2. Those are our points of interest. They appear on the graph that they gave, so that's good. I just think this explanation is could use more explanation. More explanation on how this could be done by hand. Yep, so once you got the points of interest, connect the dots, and that should be pretty good. Okay, awesome. Okay, next question. The next question on our mathematic journey is, how do we solve for y given 3, let's get a brush, 3y minus 20 equals 8y. Okay, now, can we even solve this? Absolutely we can solve this. We only got one unknown in this question, one unknown. And we got one equation. If the number of unknowns is equal to the number of equations, there's absolutely a correct answer. For now, just focus on the situation. We got one unknown and one equation. We will be able to solve this 1000%. Okay, so the first step that we're going to try to do is let's get all of our y terms on the same side of the equation. So let's say we subtract 3y from both sides. So we're going to have like minus 3y minus 3y. We'll have negative 20 because the positive 3y minus 3y, zero that out of here. We got negative 20 equals 8y minus 3y. What's 8y's minus 3y's? Is that 5y's? Sounds about right to me. 5y. Okay. Now we can divide both sides by 5, so we just get y on the right side. So negative 20 over 5 equals to 5y divided by 5, which is just, the 5 on top, the 5 on bottom. They neutralize each other to be 1. We just get y is equal to negative 20 over 5. What's negative 20 divided by 5? Is that possibly 4? For sure it is. But we got to keep it negative. Like, I know I was really positive right there, but it is a negative number. And then we would solve, we would see that y is equal to negative 20 divided by 5. Y is equal to negative 4. Wow. I think that is a question completed. Does the answer agree? Oh, it sure does. Okay. And they had the exact same strategy for handling it. That's beautiful. Awesome. So, anytime you get an equation and there's only one unknown in there, in this case, we just got our y as our unknown. It could be x, it could be a triangle, it could be any letter that you want. As long as there's only one unknown and you got one equation, I pinky promise you'll always be able to solve it. That's math magic. Isolate all the unknowns onto one side of the equation, and you should be good. Should be good to solve it. But keep in mind, you're going to want to have your equations, your unknowns, all just be like, not have powers to them. Or if they do have powers, all to the same power. You don't want to have mixed power stuff. Like if this was like a y squared on here, like if that was the case, it's kind of a different story. But don't need to worry about that for now. Sounds good? Awesome. Okay, so this above solution is absolutely correct. Not a single doubt about it. I can't find one thing wrong about it. The above solution is correct. And that's my favorite part of math. If you are right, you are absolutely right. No one can tell you that you're wrong if you're right, because then they're just going to say, oh, the math is wrong. The math doesn't work anymore. No, if you're right, you are absolutely right. You can never be wrong in math. That's my favorite part of math. Okay. Next question we got on the menu today. How do we simplify x minus 3, but all of that cubed? Well, it is pretty simple, but I'm pretty sure another rephrasal that they can be asking about this is how do we expand this out to be in cubic form? Now, to the power of 3 just means we're multiplying this thing by itself thrice. So this is just equal to x minus 3, x minus 3. Oh, well, surprise, x minus 3. Okay, now we can just multiply this out normally, and that's a perfectly fair way to handle this. So let's do the first two terms first. So we'll do that first, x and the x, and then we'll do a different color, blue, for that. And then maybe in green, we'll do these two terms, and maybe in purple, we'll do these two terms. Okay? So all of this is equal to, the red one is x times x squared. Sounds about right. The next thing is x times negative 3. That's the blueberry. So x times negative 3, negative 3x. Okay. The next thing, we got our green. Negative 3 times x. Hey, does that sound like negative 3x? Sounds like a negative 3x to me. And the purple, at the end, negative 3 times negative 3, positive 9. Remember, negative times negative. I'm positive that's going to be a positive answer. I don't want that negativity around me when I got two negatives multiplying each other. Okay, awesome. X minus 3, we can't forget that. That just comes from here. Let's simplify our this area a little bit. So we get like x squared minus, what's minus 3x? Minus 3x. Is that minus 6x? We collect the like terms. It is minus 6x. I'm certain about that one. Minus 6x plus 9. And then we got x minus 3. Okay, now we're going to do pretty much the same strategy, but doing with 3 terms, it's pretty much the same. I'm just going to move this downwards a little bit so we got a little bit more space on top to draw those arrows. Okie dokie, artichoke. Okay, let's start off with red, and we can follow a rainbow pattern because rainbows are super cool because rainbows are circles. Did you know that? That's a fascinating fact. Let's get the brush. Okay, so first we're going to multiply those two in red. We can follow orange. And we can go do those two. Okay, now red, orange, yellow. Okay, this might be a little bit hard to see, but I promise it's there. 6x times x. Roy G. And the last one is going to be 9 times both of them. So blue and indigo. Roy G. Biv. Okay, now let's math that out. Okay, come back. The first one let's do is the red one. So that's going to be x squared times x. I'll expand that out in the next one. Okay, that's the red one. Let's do the orange one. X squared times negative 3. So that's negative 3x squared. Okay. Yellow I'll actually do in black because yellow is tough to see sometimes. 6, we have negative 6x multiplied by x. I think that's negative 6x squared. Negative 6x squared. Sounds about right. Okay, now we got our green one. Negative 6x times negative 3. Negative numbers multiplied together. That's a positive. I'm positive about that one. So we got 3 times 6, 18x, positive, plus 18x. Okay, the next thing we got is blue. We got 9 times, positive 9 times x, positive 9x. And the last one are indigo, or purple. 9 times negative 3, negative 27. Okay, now let's collect our like terms. So that is solo. Solo x cubed. Only these two are x squared, so we're going to combine those. Only these two are x, and that's a solo. So we're basically going to combine our x squared terms and our x terms. Did I miss anything? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, we're all good. We're all good. Just gotta make sure. There's no harm in double checking your stuff. It's actually probably more harm if you don't double check your stuff. Okay, so first term we got x cubed. And then let's combine our x squared terms. Negative 3x squared minus negative 6 minus 6 x squared together minus 9x squared minus 9x squared. Okay, next two terms, 18 plus 9, 27. X plus 27x. And the last solo term we got here, minus 27. And that's it, and that's all. Hey, and the answer that they got, they pretty much followed the same procedure, maybe just a little bit differently. Yeah, but this is how I would do it. Like, you know, break it down into threes. And it's just like, you got to be able to expand, multiply things together that have multiple terms. It just follows the same pattern. Just make sure that you don't lose anything like this. I feel like drawing lines, if you have the ability to draw with different colors, this will certainly help you keep your calculations in line. And you can celebrate a question solved because that answer is certainly correct. Awesome. Okay, so the above solution is correct, but process is a little unclear for this particular example. Okay. Solution, Gucci. Convert 5. Okay, the next question we got on the menu today. Convert 5 millimeters to inches. 5 millimeters is half a centimeter. Yeah, okay, so because the world is a complicated place, we have developed multiple different ways to measure multiple things. Like, we know that you can measure distances in millimeters, meters, kilometers, you know, and that's like in metric, it's nice and easy. Like 1,000 millimeters make 1 meter, 1,000 meters makes 1 kilometer. But somewhere, somehow, some people decided that let's make a system where we got inches. 12 inches make a foot, 3 feet make a yard, and like 1,600 or so yards make a mile. Someone said, yep, that sounds like the best way that we can measure stuff. And till this day, we still have to deal with converting between different units because some people are very adamant on keeping their imperial units. It is what it is. We just got to do some math to accommodate that because it is easy to convert. So we're basically looking for, to do this conversion, we're looking for the number that is millimeters. Whoops. Let's get the brush. Millimeters per inch. I think it's 25.4 millimeters per inch. Yeah, 25.4 millimeters per inch. That is the conversion. Okay, now we can easily say 1 inch is equal to 25.4 millimeters. Okay, now this is going to be a very important, not only in math, but across many different subjects, is to be able to know how to cancel out units. So let's say we multiply this, like we're trying to find our number of inches that is represented by 5 millimeters per 1 inch. So if we just multiply this by 5 millimeters over, I guess 1, because it really is just 5. If you look closely, you can see that the millimeters on the top here get neutralized by the millimeters on the bottom here. Even though they're just units, if you see one on the top and one on the bottom, they will certainly cancel out each other. And I promise that's always the case. So this translates to equals 1 inch times 5. The millimeters got neutralized by the millimeters on the bottom over 25.4. Used to be millimeters, but those got neutralized out. So this is just equal to 5 over 25.4 inches corresponds to 5 millimeters. Let's pull out the calculator, the handy dandy TI-84, to figure out what that is. 5 divided by 25.4. Answer to that, 0.19685, a couple decimals later, inches. Okay, that would be our final answer for converting 5 millimeters into inches. Just make sure that you have like a fraction like this that tells you the relationship of like how many millimeters per 1 inch. 25.4 millimeters per 1 inch, or 1 inch per 25.4 millimeters. Yeah, stuff like that. You want to have that fraction, and using that you can do a unit cancellation and just multiply it properly. The units will cancel out and you should get your final answer in the proper units. Make sure you keep your units in line. If your units go on the wrong side, you'll be in trouble. Sounds good. Yep, so they got the exact same answer to the exact same decimal depth, so the above solution is good. Above solution is good. Now, wouldn't this all be easier if the entire world just agreed to use centimeters, meters, and metric measurements. Wouldn't that be nice? Wouldn't that be nice? Okay. So the next question on our menu today, what is the value of log 0? Oh, this is a spicy question. Log 0. Let's rewind for a second and think about, what does log even mean? Like, we're not talking about lumber here. We're not talking about chopping down trees to get logs. We're talking about logarithms, the mathematical function. So suppose we have something like this. Equals what? Okay, suppose we have something like this. Log, the base can be base of, let's say of A is equal to C. This basically means that a base to the power of C is equals to A. Okay, let's do that down here. If the log doesn't specify a base, immediately know that it's base 10. I'll just write that off. Base 10 if nothing specified for base. Okay, that's important. So given this, we're basically trying to find that log depacked along these lines is basically saying, like, 10 is the base, right? So 10 to the power of something is equal to 0. Now, what does it mean to do to the power of? To the power is to multiply it over and over again, right? So 10 to the power of 2, that's 10 times 10. 10 to the power of 3, that's 10 times 10 times 10. 10 to the power of 5 is 10 times 10 times 10 times 10 times 10, 5 times. Is there anything... Okay, let's think about this for a second. If the result of a multiplication is 0, one of the things that you multiply has to be 0. There's no way that you can just multiply two things together and get 0 unless you're multiplying zeros. So it's basically saying 10 multiplied by itself, how many times is 0? What? Does that make sense? How could we possibly multiply 10 by itself over and over again to get 0? It don't make sense. So really, the answer of log of 0, it don't exist. Can't happen. No, not happening. Not working out. No. No answer. And you'll actually see this if you plot a logarithmic graph. Logarithmic graphs typically look a little something like this. So you have your y, you have your x, and let's say the log is so that will be 1. It's going to look like this. The closer and closer you get to 1, to x equals 0, the closer and closer the smaller and smaller the y value is going to be. Like, it's going to go straight down. X cannot be 0, even when x is like, 0.0000001, like extremely close to just being 0. Like, it's going to have a massive, like an extremely deeply negative y value, but you can never get an x equals 0. It's just not possible. And x can also not be negative for or the result of a logarithm cannot be there's no like negative part to a logarithmic plot. Okay, so just know, if the log of 0 exists, not happening. It don't exist. There's no answer. You can't handle this. You see log 0, you say, get out of here. You're not even real. There's no solution to you. Or you can be a little bit more friendly, but I like to be aggressive with the numbers. You dominate the numbers so they don't dominate you. The above solution is good. Awesome. Log 0, get that out of here. I don't want to see you anymore. really just gets me fired up. Really fired up. Okay. That actually was our last question. So I'll just go back to strict my webcam. I think the sun was up when I started the stream, but time flies when you're having fun. So those are all the questions that we're going to cover today. If you enjoyed today's Q&A and would like to be notified when we do this next, please hit the subscribe button and ring the notification bell below. If you'd like to submit your own questions, please visit the links in the description. Remember to leave a like and a comment if you enjoyed this or if you have any comments, and share this video with your friends if you think that this will be helpful to them. This has been Millan from OneClass. I hope to see you again soon, and happy Halloween. Hopefully if you're celebrating Halloween and you're dressed up like me, maybe in a spooky costume, enjoy your Halloween safely, and remember, it's a tough time right now. We have to stand up and protect our community. Celebrate safely if you are celebrating your Halloween. Otherwise, I hope you have a great evening, and I hope you get more treats than tricks.